For today's enrichment activity, we are going to look at solving exponential application problems. We're going to look at three types of exponential function applications. These are three very common applications, and the first one is population growth. So here's our problem. The population P of a town is 475,000 and is increasing at the rate of 4% per year. Find what the population will be after 15 years and when the population will be 600,000 people. So how do we go about solving this? For our solution, let's try to build a general function by examining the population of the town for a few years. Let's start with our initial population. We have 475,000 people. What happens 1 year later? We know that we're still going to have that same 475,000, but now we're going to add some growth to that. We are going to grow by 475,000 times 0.04%. That's what our problem says here and here. If we simplify this, we are basically saying that we have this 475,000 and we're going to grow by 100% of that plus 4%. So we can write this as a more simplified model, 475,000 times 1 plus 0.04. The 1 is the 100% of what we had, and 4% is our growth on that. Putting that in our calculator, we would end up with 494,000. Let's move on to year 2. Now, at the start of year 2, we have a population of 494,000 people, which we know we're also going to grow by 4% that year, or in year 2. And simplifying this, we can say that this is the same thing as 494,000 times 100% of what we have plus a 4% growth. Plugging that in our calculator, we end up with 513,760. As you can see, this is going to be a little bit cumbersome to get to 15 years. So how can we start with our initial population and create a general equation or create an equation for the year 2 to come up with the same answer? Well, we know that we're starting with a population of 475,000. So let's think about what we're doing. We're taking 100% of what we have plus 4%. And if we consider that this has now been 2 years, if we raise this to the second power, we will end up getting the same answer that we did if we did it manually. So let's look at year 3. In year 3, if we did it the previous way, we would say that we have 513,760 people plus 100% of that times a 4% growth rate. In other words, 513,760 times 1.04. I'll add the 1 and the 0.04 together. And if we put that in our calculator, 534,310. Again, very cumbersome. So looking at our equation, we can go back to this initial equation. 475,000 was our population to start with, times 1.04. And how many times are we doing that now? We're doing that 3 times. And if we put that in our calculator, we end up with the exact same value. Now you can start to see a pattern arise. So let's come up with a general function for X years. What can we use for 15 years where we don't have to do this every single year? Well, we can say our initial population, or 475,000, times 1 plus whatever our growth rate is, raised to the X amount of time, or T for time, and that will give us our answer. Let's do our calculations. So if we substitute X with 15, because we want to know what the population is going to be after 15 years. If we plug this into our calculator, so in other words, we're finding the population at 15 years, we would plug 1.04 raised to the 15th power times 475, and we end up getting 855,448 people. And you can try the math to confirm. So what about the second part of this problem? When will the population be 600,000 people? So in other words, we have 600,000 is equal to 475,000 times 1.04 raised to an x value, which is time. Since we have not started doing logarithms yet, we cannot solve this algebraically. But what you do know how to do is put this in your calculator. If you put in your calculator that y1 is equal to 600,000, so you're graphing a horizontal line, and you put in your calculator that y2 is equal to 475,000 times 1.04 raised to the x power, you'll get your exponential curve. Your graph, let's go ahead and look at the graph. Here are two functions. So we have y equals 600,000, and then we have our y equals 475,000 times 1.04 raised to the x power. Their intersection point right here will give us our answer. Remember that our x-axis here is going to be time, and our y-axis is population. So it looks like we'll reach a population of 600,000 people in approximately 6 years. So in this case, we can say 6 years. All right, let's look at problem number 2. For this problem, the number of bacteria present initially in a culture is 2,500 and is observed to double every hour. Find the number of bacteria present after 10 hours. How long will it take before there are 200,000 bacteria present? Well, now that we know how to do this, we can find our solution in much the same way. We can use our same formula that we use for population. We can say that P of x is equal to our initial population, P sub 0, times 1 plus whatever the rate is, raised to some increment of time. We'll call that x. If we realize that if something doubles, it is the same as exhibiting 100% population growth, therefore the population will be 5,000 after 1 hour, which is a growth of 2,500, which is 100% of the initial population. Then since 100% as a decimal is equal to 1, then we know that our rate would equal 1. So let's fill in our equation. This then makes our equation, P sub x is equal to our initial population, which is 2,500, times 1 plus our rate, which we said is 100%, or 1, raised to the x power. And we can even write this as 2,500 times 2 to the x to get our actual equation. Then after 10 hours, so in other words, we're putting 10 hours in for x, we would substitute 2 raised to the 10th power. We would end up in our calculator with 2,560,000 bacteria. To find when there are 200,000 bacteria present, again, in your calculators, you have y1 would be equal to 2,500 times 2 to the x, and in your y2, you'll plot the amount they're asking for, 200,000. Graphically, the intersection point ends up being at 6.32, 200,000. So in about 6.32 hours, or approximately 6 hours and 19 minutes, if you take the 0.32 times 60, there will be 200,000 bacteria. Notice in this problem, since the population doubles, the base of our exponent, this 2, represents doubling, 200%. Let's look at our last type of exponential function for today, and this is radioactive decay. So we know that our initial amount is going to go down, so we're going to have a fraction for our rate rather than a number greater than 1. In this problem, the rate at which a radioactive substance decays is called the half-life of the substance. The half-life is the amount of time it takes for half of the substance to decay. A certain element has a half-life of 14 days. In other words, in 14 days, only half of it will be left. And there are 6.58 grams of it to start with, the initial amount. How much of this element will be left after 50 days? And when will only 1 gram of this element be left? Again, we can use the same formula that we've been using all along. Now, if we realize that since we are losing half of the amount of the element each half-life, then we know that our R value in this case, since we're losing, has to be a negative 0.5 or minus 50%. If we want X to represent the number of, or days, basically, we will have to modify our exponent to represent how many half-lives are in each day. Since 1 half-life is 14 days, then each day, so X, is 1/14 of a half-life. So each day is 1/14 of a half-life. Now our exponent then will be X over 14. Given this information, we can now create an equation. We start with an initial amount of 6.58, that's our p sub 0. Now think about this in here. We have 1 minus 0.5, so this leaves us with 0.5. Thus, our base is a fraction between 0 and 1, which means we're going to have a decay problem. And here's our time. To determine how much of the element will be left after 50 days, all we need to do is plug in our 50 into our adjusted time. So we would have 50 over 14. And when we put this in our equation, we can see that we will have 0.55 grams of this substance remaining. Again, to find when only 1 gram will be left, solve graphically to find the point of intersection. And the point of intersection, if you want to try this on your calculator, ends up being 38.05, 1. So approximately after about 38 days, there will be only 1 gram of the element left. Note that since it is a half-life, the base of the exponential equation equals half. And you can see how that relates. And that is the end of the 3 examples for different types of exponential function applications. You'll be using these examples to solve 3 of them on your own.